Everybody, this is TATA for now. We have Joey, Toddy, Aaron, Alex, and Tatiana, actually. So Tatiana and Toddy. So if you get confused, which you don't. So Joey's going to go ahead and start us off.
Okay, today we're gonna talk about the wastewater discharge in creamery. The creamery performs CIP and COP on their equipment each day. In order to clean their equipment, they put alkaline product, which is soap, in both CIP and COP system. Those water with soap has high pH that cannot directly pour into the drain. So they need to add neutralizer to neutralize it. So now I'm gonna talk about the CIP and COP system a little bit. Here's the CIP system. CIP stands for cleaning in place. So what they would do is they first put the rinse water to rinse off the residues in the tank, and then put the soap to clean it, and then they put neutralizer to neutralize it, to neutralize the soap water, and then drain it. Yeah, like this. Okay, next is COP. COP stands for cleaning out of place. So what they would do is, firstly, they rinse off the equipment with tap water, and then they put equipment into this COP tank, and they add soap, and then let it circulate for a couple minutes, and then add neutralizer, and then drain it. So the goal of our project is to reduce the amount of money spent on neutralizer at creamery. And why? It is obviously to see that any company, the goal of any company is to make profit. So reducing the cost of neutralizer will allow the creamery to increase its profit, and then use this money to make improvements in other processes. So our project is focused on the wastewater produced by COP and CIP system. The reason why we choose these two systems is because that's the two main places that neutralizer will be used. Hypothesis. Based on the information above, we make two hypotheses. The first hypothesis is we assume the wrong amount of neutralizer is being used in COP and CIP system. That will cause unbalanced pH at final rings. And based on that, if that's our case, we need to correcting the amount of neutralizer used in both systems. And then we assume the wrong neutralizer is being used in both systems. So based on that, it will cause the inefficiency of neutralizer, which means you will need to add more neutralizer in this process. And then based on that, we probably need to change the neutralizer. And then next is Alex.
Alrighty, so I'm going to talk about why this is an issue for the creamery, and then go into our measurements. So this is a problem because the EPA is the Environmental Protection Agency, and they mandate that any water that you're putting down the drain or any solution needs to be between a pH of 6 and 9. If you have it too high or too low, you'd be harming the environment. And so we need to make sure that we are putting down water that is that's in their specs, basically. So why are we measuring the pH? Like I said before, it's what the EPA uses to tell if it's okay to drain water. So we'll measure the pH to make sure that our water is within that range. And then we can also find a good solution, whether it's the right neutralizer, using less neutralizer or more, based off of our pH of the water that we're draining. Alrighty. So we collected samples from each drain. There's a drain that both the COP tanks in the creamery drain down. There's a drain for the CIP system in our CIP room, and also a drain for the CIP system for the pasteurizer. So what we did is we collected data 8 times for the CIP process and 5 times for the COP process. We thought that was enough to give us an idea of what the everyday pH average is. So we took those, we collected the samples every 5 minutes for 30 minutes each time we collected them, so it gave us more than more than 8 for one and 5 for the other. We actually had what would that be? 6 times 8 times 5. And I'm not going to do math, but you get it. So they were taking a triplicate to have better pH, and then we averaged the pH for each triplicate, and then we used QI macros to create control charts. So this is kind of an example of one time that we took data from the CIP. So as you can see, at 5. Oh, okay. So here's the 8 times we took it from the CIP. You can see that we have pH for every 5 minutes through the 30 minutes, and as you can see, it drops or goes up and then drops back down as the neutralizer is added for the CIP system. So that's just an example of our data table. And then this is a COP, kind of same deal. As you can see, it starts high, drops down as we go along. So.
All right, this is basically an overview of the information we got from our measure phase. So this is a graph of all the main averages for each given day that we have. And, as you can see, we're kind of sitting around, somewhere we're a little bit either below 9 or above 9 as an average between all of the samples of pHs. And that was for our CIP. Our COP, we didn't get as many measurements during the measure phase for the COP, but we still got Monday and Tuesday measurements, and they're all, once again, hitting right about 9 as a total average. Now, we decided to use an X-bar chart. Now, the usefulness of X-bar charts is they allow us to see the distribution of average mean data over a span of limits that we decide based off of a center line average. So our center line is the grand total average of everything, all the samples put together as one. And then these control limits, the lower and upper, are basically a calculation of either plus or minus the correction value multiplied by the average range. Now the correction value is just a simple, factor that's created in statistics to account for error, either in range, standard deviation with a varying subgroup. So in this particular case, the upper limit ended up being about 10 pH, maybe 10 and a half, and the lower being about 8. And the actual moving line is the data plots for each given time increment. So right as we started, 5 minutes, 10 minutes, et cetera, et cetera. And the biggest thing I want you to notice about this chart is that, once again, we hit right around 9, and then as the neutralizer is added to the CIP systems to wash, it starts jumping up a little bit above what we would consider a control. And moving on to this, this R chart. An R chart is very similar to an X-bar chart, except this one only accounts for the range in specific. So the center line is basically the average range between all the samples, and the control charts are roughly the same, except this time it's multiplied. A correction factor accounts for the standard deviation multiplied by the standard deviation. And they ended up being about between 6 and 0. So we're having an average range of about 6 pH between all of our samples, which may not be the best target for trying to stay in control. And though, based off of this, we're only saying maybe a variance, of about 2 pH between all the samples, given at each time increment. Our COP was much more accurate, or I should say precise, and that most of the averages hit right around the center line, which is about a 9 pH. The biggest difference I want to point out with this particular X-bar chart is that the control limits are much wider. So we had a little bit more of a range on our samples, which we'll see in our R chart. As you can see, the range is now about a 15, which is pretty large range between all of our samples. Now, we didn't collect as many samples, so it's possible that we just had too clumped of data, and so outliers moved our limits around a little bit too much. But fortunately, our average range was only about 7, and they kind of popped around a little bit. And what we concluded from our measurements is that, one, we really need to take more measurements to ensure before we start analyzing our data. And the general consensus is the pH of the water was going down the drain was a little bit too high. And then we need to collect more data for each of them, and afterwards we use statistical methods to determine whether the process was in control or not.
So now we want to move into. So now that we got our data, we needed to check to see if we had any kind of statistical evidence showing that we needed to make some process changes. So on the different types of tests we decided to use we decided to use process control, which is a way to measure the limits. It shows whether our process is within the limit of the legal guidelines in this case, and Tatiana will talk about that in a second. But what I'm going to start out talking about is an Anova test. What we wanted to check to see is if that's the new data. If you want to see it, there it is. You can glance at it. Basically, what we did was section it off into different days for an Anova. But what I want to talk about is the Anova that we decided to do. We wanted to see if there is a difference between people, the CIP system and the COP system. So maybe if we needed to, we could just work on one first and then the next to try to see if we can make a little bit of a profit change from there. If we can fix one, so like for instance the COP is different from the CIP, we can work on one first and try to fix that up. Or see if there's actually a difference between the days. Maybe one day that there's a difference between it, so maybe work on training people to work the COP system a little better on one day instead. And so we have the two different factors that we're looking at, and so we have a two-way Anova to determine whether or not we have these differences or interactions between these differences. So here we got is an Anova table. There's lots of numbers, lots of data, but we only need a couple numbers from it to that we're looking at. So what we have is an F value and an F critical value. The F critical value is a statistical number that's calculated. We use Excel, and so Excel will calculate for you, or there's data tables that will calculate it. And what that shows is if our F value from our data is smaller than it, then there is no significant difference between two data points. So for instance, in this case, we discovered that our CIP and our COP system have no statistical significance between each other. So that the data sets we're getting from both are actually pretty much the same. But if we continue to look down, the days, our F value here is much larger than our F critical value. And so what that is showing is that there is a day, we don't know which day it is, that there is a difference between the numbers that we're getting. And so in order to tell which days are different, we had to continue on and do a kind of a post-test on those numbers. And the post-test that we decided to use was Fisher's LSD. Fisher's LSD is just a mathematical equation, and what it is a way to compare days to different days. And the Fisher's LSD had it's not on there. So our Fisher's LSD number, it's a number, was 1.1, and so any values that are above 1.1 show a difference between those 2 days. So for instance, Wednesday over here and Monday have an average difference of 1.24. And so what that means is that those 2 days, since it's greater than our Fisher's LSD number of 1.1, are different. So Monday and Friday had the same numbers, and Wednesday and Friday had the same numbers, but the only 2 days that we had any difference from when we took our data was Monday and Wednesday. And so there could be a lot of different reasons for that, and we were thinking that the reason that it was might be is an operator on difference between Monday and Wednesday. So, and I think next is a property test.
Thank you.
Welcome.
Well, this is our capability, process capability and capability index we made. First, I like to explain the process capability. Erin already talked about the process control, and we saw that we have points out of control. But you can have a process that is in control but is out of specification. That is different. And as Alex Agnew said, the limits for the pH for water discharger is 9 and 6. So we calculated the process capability to see if our process, even that is out of control, is within the specifications. And we calculate the process capability, that is 6 times sigma head. Our sigma is 1.5, so our PC is around 9.04. That means like how wide our data can go for both of them. And then we calculate the CP, that is the upper specification limit minus the low specification limit divided by 6 sigma, 6 standard deviation. And we found 0.299 and 0.332. And for CPK, that is the up specification limit minus the average divided by 3 standard deviation, we found minus 0.029 and 0.102. And what that means, if the CP and CPK is less than 1, that means that our process is out of specification. And as we saw at the beginning with Erin, that all the average was above 9, only a couple of ones were about 8 point something. But this is one just to confirm to us that our process is out of specification. So here is the chart for the CIP for the process capability. And to be within the specification, our data should lay between these here. And we are seeing points outside the specification. And for COP is the same case, should lay in here, but it's that we have some points out of here. That means that our process is also out of specification.
Analyzing our results, we can conclude that our process is out of control because there are some points outside the control limits on the X bar and R chart. And through our results from the two-factor ANOVA, we can say there are difference on pH between Monday and Wednesday, and our capability index is less than 1. So our process is also out of specification. Our data collected showed us a pH average greater than 9. But according to the EPA, Environmental Protection Agency, say that our desirable pH should be between 6 and 9. So we have 3 suggestions for the future and try to solve this problem. And we can find a way to bring down the pH of the neutralizer. So we can add something such as acid with the neutralizer and try to bring down the pH of the neutralizer. We can reduce the variation in the data by using a mixer. Our pH variation is large, so we can try to reduce this variation by using a mixer. And we can find a new neutralizer which will work better and will be cheaper. Any questions?
Have you guys researched any neutralizer that could do whatever you guys want that it does?
Actually, we didn't because we did not have time enough to continue the project in the analyzing proof phase.
In the beginning, why did you take different amounts of measurements for COP and CIP?
Mostly availability. The time in which we were able to take measurements was completely based upon our own schedules and the time we could actually enter the creamery to take measurements. We attempted to correct for that mostly in the second time when we started analyzing our data. But for the original, we just kind of wanted to get a ballpark shot of what actually was going on so that when we took further measurements, we kind of knew more what we were looking for so we can make more accurate measurements later on. Yes, sir.
What neutralizer is being used now?
It's a citric acid.
Citric acid.
On both the CIP and the COP?
Yeah, same neutralizer.
I think it was Joy who kind of went through how the CIP system worked. So when you wash a vessel, what pH are you hoping to reach to adequately clean the vessel?
So when you put the vessel in the washing tank, when the water fills above the equipment, we start to add the soap. And when we took the pH, it's around 10 or 11.
Needs to
10
be higher than 11.
Yeah, and then we add neutralizer. It's basically it reached like 7 or 6 when we're ready to drain.
However, we really want the alkaline soap pH to be above, 11 or 12 to effectively kill microorganisms and clean the tank. But before it's turned down the drain, we want to drop that pH so that it meets EPA standards.
And what type of cleanser do you use to prevent buildup of biofilm and proteins on the stainless steel equipment?
It's isn't it the chlorine sanitizer that we use? Or are you talking about the soap that we use to, actually in the CIP system?
Normally, when you're cleaning stainless steel equipment, you do want to have a little bit of chlorine generally in the soap.
Yeah.
But once you've adequately washed it with soap and heat and agitation, then typically you would add an acid to make sure you don't build up biofilm and proteins on there. And hopefully in our CIP system we are adding an acid.
Citric
That would be
acid.
something. That would be
Yeah,
something
that's
to
what, okay, I
investigate.
misunderstood your question. I thought we had already answered it, I guess. That's,
And so
Okay. Any other questions? Yes, sir.
Just go back to the Anova chart. Yeah, that one.
Cool.
With your, so you chose what is a p-value for significance of being 0.5?
0.05.
0.05, and that's why we ended up with, on that first row there, 3.28 and a p of 0.07. So so it's actually the p-value that actually gives you as far as your confidence. Is that correct? As far as in your answer, your
baby.
testing hypothesis?
So basically, this was our confidence was 0.05. So that our data, we knew that would lie within 95% of the data. I didn't use the p-value to determine a significant difference, though. We were just using the F-critical values.
Yeah, but the F value comes from the p-value.
You don't need to. Well,
See,
no.
if I increase that, to put a different thing in there, then my F critical would change.
Well, I did. What I did was actually use since you use the p-value, yes, for it,
To generate the F.
to generate the F critical value.
Okay.
To generate the F value, you use your error
Right.
and your degrees of freedom.
Okay.
So, so I guess in a sense, yes, our F critical value was determined by our p-value, but the p-value used to get that F critical value was a 0.05.
Okay.
Does that answer your question?
Just checking you out there.
Okay. Thanks, Frank. I appreciate it.
Just a clarification, so all of the sampling was taken at the drains?
Yes.
Not,
Yes.
not inside the tanks, but
At the drains.
At the drains specifically. So right as the disposal was going straight down the drain at the point at which the EPA would care about.
So that's why we suggested maybe getting maybe some more agitation in it, because the pHs do lower down. If you saw, it does lower down, but it's very high.
Discharge does that pretty
Oh,
well.
I just did it. No, that's good. We're good.
Oh.
Any other questions?
I have a couple of questions. So if you go back to your first data chart, there we go.
This one?
No, the table. Okay. So there was ×6. That pH starts low and goes up. What's happening there?
Well, I mean, what we could theorize that it's just random chance, or there is a possibility that at the moment we took the measurement, some maybe as it was getting rinsed, some leftover bits of the raw alkaline soap that wasn't necessarily homogenized with the citric acid might have hit the drains at this particular point in time, which jumped the pH up suddenly when we took the measurements.
Or
That's
we
a
could have put the
possibility.
data in the table upside down. That
Kinda
also
looks
could have
like
been
that.
it. I think that's probably what happened.
But you also have this other thing at time 5 where you have, up and down. So,
It happens at
That's
times too as well.
45.
Yeah.
so maybe you just didn't wait, 30 minutes wasn't long enough for it to come back down.
Are any of these rinses longer for any reason? Like is ×6 a longer rinse, or maybe time 5 was a shorter rinse or something like that?
So the answer to that question is the rinses themselves, we didn't stay for the whole rinse cycle of it. We were able to get a 30 minutes rinse cycle, but as the rinse cycle lasts anywhere between 30 to 45 minutes.
So it is possible that the moment when we took in measurements was either near the beginning of the window or the end of the window. And that's why the data maybe looks so varied.
And my last question is, I know you guys didn't have time to look at specific acids or anything to drop the pH, but do you have any recommendations for properties that that particular neutralizer should have to be used in this system?
I believe that a neutralizer with a pH less than the pH of the acid citric would be a good choice, since if you have a really low pH and you put with a high pH, they will balance, and it will be, I hope it will be between the specification limits, since that the pH of the acid citric is not working to bring the pH of the water within the specification.
The only problem if you put something at really high pH with really low pH is you can have a very exothermic reaction, and you don't necessarily want that to happen.
Another thing you could do is use a acid that it goes into a diprotic system when mixed with a base, and so there's a potential for less of an exothermic reaction because it's having smaller oxidation of the acid.
That'd be food grade.
That'd be good.
That is true. That is true. However, we're more concerned about EPA grade.
is there any residual chlorine left in there when you're adding the neutralizer?
I don't think we would know unless we were to analyze the data with a like an HPLC or gas. I don't know, gas chromatography wouldn't be able to do it. I don't think, but we didn't look at that.
That would be something we could do in the investigation further on to improve.
I don't think there's a chlorine left in CIP tank because I took out most of the CIP data because they rinse off like all the equipment and the tank was being rinsed before they put the equipment.
Do you have any more questions after that?
All right, anyone else have any other